Thanks. Well, hi, I'm Bob Grant. I work at Enthought here in town. And I'm going to talk about DistArray, which is addressing a similar problem to what I caught in the last talk. So, in a nutshell, distributed arrays for Python. What we're trying to do is reuse everyone's mental model. Everyone's familiar with NumPy arrays. Everyone's familiar with working with NumPy arrays. We'd like to give you a high-level data structure, high-level object that you can work with that looks a lot like a NumPy array, but happens to use IPython Parallel or MPI to give you distributed computation, to let you distribute your data and push your computations close to that data and work with it. So it's built for data parallel problems, a lot like problems that you would want to use NumPy arrays for, but say you have a NumPy array that's bigger than you'd want to use on a single core or a single machine. It's an open source project. It's BSD licensed. It's on GitHub. We'd love if you came and checked it out. And it works on Python 2 and 3. So just a little bit about the people who worked on it. We started with a code base developed in, I think, 2007 or 8 by Brian Granger called DistArray, and we've been working on it for a couple of years. A team led by Kurt Smith at Enthought. I think he's in the audience somewhere. And Blake. I think I saw Blake around somewhere, too. So DistArray is built on these widely used libraries. We're not implementing all this from the ground up. We're trying to reuse what we can. So we're using NumPy. We're building on IPython Parallel, MPI for Py, and MPI, and optionally libraries like H5Py for distributed or for parallel I/O of HDF files. And aside from that, we're very keen to work with other existing scientific libraries like Trilinos, Global Arrays, that have their own notions of distributed arrays. So we're working with Bill Spots, who's working on PyTrilinos, and Jeff Daly working on GAIN. We'd like to work with other libraries. We have something called the Distributed Array Protocol, and it's well documented. And we hope this makes it easy to take dist arrays and give them to Trilinos or Global Arrays or go the other direction without copying data around. So we're really trying to leverage the existing ecosystem. So NumPy arrays. These are these great things, this foundation of the scientific ecosystem in Python. It gives us this multi-dimensional, this n-dimensional array data structure. It gives us this nice view of data that's stored efficiently in memory, and we want to build on this. And in fact, dist arrays use NumPy arrays under the hood. So what is a dist array? A dist array is basically a proxy object. This is our surrounding dist array here. And it's made up of sub-objects called local arrays. Each of these local arrays, that can be on your machine or distributed, are wrapped around NumPy arrays. This dist array is this global view of your potentially large array. Each of your local arrays contains a chunk of that data as a NumPy array, and hopefully it makes it easy for you to work with this as if it were a single NumPy array, this familiar NumPy interface. And so one of the things that we built on is IPython Parallel. So if you're not familiar with IPython Parallel, it's come out of the IPython or the Jupyter project, I suppose. It gives you some of what we're looking for already. So we're building on top of this. So with IPython Parallel, you can spin up a number of engines or a number of worker processes, and then you have a client process that talks to these worker processes over 0MQ. So with IPython Parallel, you can create some data on your client. You can push the data out to your engines, do some computations on them, pull the results back, things like that. And optionally, you can spin up your engines with MPI, so you can use MPI to communicate between your engines. And so we're building on top of this. And where dist array would live in this kind of infrastructure is the dist array itself, the high-level proxy object, would live on the client. It gives you something that looks like a NumPy array. And the local arrays live on these worker processes on these engines. And so you have this dist array, and you would do NumPy-style operations on it, like sign or reduction operations or things like that. And the dist array and some of the associated infrastructure would push that computation down to the engines for you, do that computation locally, and give you a new proxy object up at the top, a new dist array, probably, to work with. So enough of high level. Let me pop over to some code and show you what this actually looks like. So I mentioned that, at least by default, this works on top of IPython Parallel. We recently created an MPI-only version, so if you don't want to install IPython parallel or have other objections to using 0MQ, you can do it all with MPI, but usually you start up an IPython parallel cluster. We have a little wrapper around that called DA cluster. I'm going to do some imports. And I'm just going to start with a NumPy array and try to compare and contrast what the API looks like. So I'm going to make an example NumPy array, just a simple 4-row, 5-column array. And these have attributes that we're used to. NumPy array has a D type, its internal data type, number of dimensions, shape, item size, these things that we've seen before. So one of the easiest ways to make a dist array is to, with a little bit of setup, that I'm not going to talk about here, is to make a dist array from this NumPy array. So from this context object, this is a little bit of a manager or a namespace thing that kind of manages the communication between the client and the engines in dist array. It keeps track of things under the hood like where your engines are and the client object from IPython parallel, things like that. But we can make a dist array by calling context.fromArray our NumPy array. This one line is doing a bunch of things for us. It's taking our NumPy array, it's splitting it up into chunks. It's deciding how to do that right here. You can actually be very specific about how you want your data to be split up and farmed out. And pushing that data out to the engines and giving us this dist array object to work with on the client side. So if I print out, if I look at the repr of this dist array, I just get this dist array representation. So all our data is out on these engines, not necessarily where we are on the client. So we just have this representation like this. Now if I want, I can pull all that data back. I can call this getLocalArrays method to pull the data back to the client and look at it if I want. But generally, we're going to leave the data on our engines. We're going to work with it there and pull out summaries or other representations, reduced representations of that on the client. So, but aside from that, dist arrays have a lot of similarities to NumPy arrays. At least they look a lot like NumPy arrays. They have a D type. They have a number of dimensions, shape, item size, etc. But they have a few different things. So dist arrays have a context. As I mentioned, there's this context object that manages which engines, which workers this dist array data lives on. And this targets attribute explicitly says what those targets are. There's also a distribution object. This is heavily inspired by distributions in Trilinos. I see Bill Spots is here too. So you can control how your global indices of your array get farmed out, get mapped to these local arrays. So we have this dist array. What can we do with it? Hopefully, we can do NumPy style things with it. So we have universal functions. We have ufuncs. We can call, just like we can call numpy.sign on a NumPy array. We can call distarray.sign on a dist array and get back this new proxy object. We can add two dist arrays together, get a new dist array. But all this is happening client side. We also have reduction functions implemented, so sum, min, mean, max, things like that. So take a NumPy array or a dist array and reduce it to a smaller set of numbers. And also indexing and slicing. So one of the great things about NumPy arrays is that we can do this slicing operation. We get a view on our data that allows us to modify the view that writes through and modifies the underlying data. So even though the data is distributed, we can do this global style indexing. So on our dist array, we can do NumPy style indexing, grab a single value, or we can use slice style indexing and grab an entire column out, which is it's a new NumPy array, but it's a view on this original data. So if we write to it, it writes to our original NumPy array. So I'm going to skip over distributions, but dist array distributions are a very handy thing. You can say, with some high-level objects, how your data is distributed, block cyclic, unstructured, if you're familiar with these terms from something like ScalaPack. Or you can just be very specific and say, I want these indices to be on this engine and these indices to be on this engine. Dist array gives you control over that. But I wanted to mention a couple of the methods we have for pushing your computations to your data. So you might want to have this high-level view, just treat it like a NumPy array, let dist array do what it wants when you do a computation on it, push the computations for you. But sometimes you want closer control, or you want to actually work with your local data. So with this notion of our context, we can write our own function like this, very similar to something in IPython parallel, to apply our own function to each of our local chunks individually. So this is just a simple example, writing a random function that on each engine imports NumPy and gives me back a random integer. So it's pretty simple. But something you might want to do, instead of working on this array at a global level, you might want to work with it on a local level. For example, by taking the variance of each one of my local arrays. So working with each chunk locally instead of this global view. As Kurt likes to say, this array gives you this global view with local control. So we can write our own function and then apply this function on all of our bits with this apply method. Or a little bit more conveniently, we can register a function in our context, which basically means if we have a function like this, we can register it with our context, push it out to all of our engines, and then whenever we call this function that we've created, it will be called locally on all of our engines for us. Then later on, if we want, we can pull the results back. So as I mentioned, we can do MPI-only execution. If you don't want to use IPython parallel, you can run in more of a batch style and have all the computation be done, all the communication be done with MPI. And I definitely want to mention this distributed array protocol, inspired by the buffer protocol. This is basically a method on our local arrays that gives us all the information, hopefully, that we need for another library like Trilinos to take a dist array, interpret it in its fashion, and use that data without copying it over. And this is one way we hope to work with other scientific libraries, pass data back and forth, and maybe rely on Trilinos for its already built-in sparse linear algebra capability instead of implementing that in dist array. All right. So I've shown you what we have implemented already. There's definitely plenty more we'd like to do. There's some neat things in the Dask talk just before this that would be nice to have in dist array. What we've been using under the term lazy evaluation. So if you're working on this high-level dist array and you did a loop on it, it would be nice if instead of having a communication round trip to the local engines for every computation, it queued those up, maybe did some simplification on this computational graph, pushed that to the engines where it was done, and then brought back, instead of having a round trip for every computation. We have some basic redistribution capabilities. This gets more complicated with complex distributions and data layouts. And we definitely want to emphasize our interoperation with other libraries like Trilinos, and that's something we're working on right now, as well as things like distributed broadcasting and fancy indexing is not something we have yet, additive core computation, so there's definitely room to work with some other packages for some of these roadmap items. All right, so again, check us out on GitHub. We have some docs up on Read the Docs, but we'd love if you tried this out on some distributed array type problems that you have and tell us how this fits your problem and how it doesn't. Thanks.
You showed an example of starting with the data in a NumPy array on the master.
Right.
And then pushing it out. Do you have ways of just originating the data on a set of workers if it's already there, so you don't have to move the data through the master at all?
All right. So the question was, in the example I gave, I took a NumPy array on the client, or whatever you want to call it, and made it into a dist array and pushed out all the pieces to the workers. Is there a way to not have to push that data? Is there a way to create the data or load in the data on the workers? And there are a few ways. So you could, with NumPy, as you would in NumPy, you could create an array, some of the built-in functions. So there's dist array random functions, for example, to make a random array that's already on the disks. Or a more common thing you might do is load in that data on the clients with one of our I/O functions, which I didn't talk about, like loading it in parallel from an HTF5 file or from a NumPy file even. So loading it in on the disk or getting it from another library like Trilinos.
I was curious about, so you support a lot of models for high-frequency arrays. I
We-
was curious if you could talk about so that's something that could potentially add a lot of complexity.
Yeah, and so the way we've taken inspiration from things like ScaleAPEC, where you have these defined distributions like block cyclic, and let's see if I have a couple of slides. So you can, for example, I didn't talk about making your own distribution, but you can, for every dimension, you can have a different distribution in dist array. So you could have both this both dimensions be block distributed, in which case you'd get an array distributed among 4 processes like this. Or you could have one array, one dimension with a cyclic distribution. Are you familiar with block and cyclic and distributions like that? So these are just sort of pre-canned ways of distributing your data with a few different names. Either taking ranges and mapping them to processes, or round-robin style mapping each of your indices to a different process. And then, the most general way of doing that would be this unstructured, where you can say exactly, I want this list of indices to live on this engine and this list to live on this engine. So you can be very specific about how that works. Did that answer your question?
I guess I was curious about the, do you need, like, other actual use cases supporting all these different types of distributed chunks? Or, like, is that worth that complexity?
Well, so there's a default, so hopefully you don't have to deal with that complexity unless you want to. But I mean, one common reason you'd want something like this is it's kind of an easy load balancing method. So if you have a problem domain where in this chunk there's not going to be very much work done, but in this chunk lots of work is going to be done. If you did a cyclic distribution, it would maybe distribute that work more evenly. So we're trying to make it easy to do easy load balancing, and if you want more control, maybe you can specify exactly where all of your data goes.
We did have discussions, though, with interested users, right, or like Trilinos and IPython, and we all kind of came to agreement on, what the general approach should be, supporting whatever.
All right. Any last questions? In the back?
So you did mention that you do everything for communication between different engines. I was just wondering what are the default persistent settings that Array uses?
Are you asking about the default settings just Array uses for 0MQ communication?
Not as you have like persistence of different machines.
Sorry, I couldn't quite hear you. I'm a little stuffed up.
Persistence of these different machines of like pre-computed results or like EMC results. Like what are the default settings?
I'm sorry, default settings for
So
persistence?
like are they like persistent on each of these separate engines or
Oh.
are they kind of like totally in memory?
They're totally in memory by default. So yeah, nothing is persistent by default. We would love to add in some support for out-of-core computations in the future. All right, thank you.
Okay. Let's give it a